Hi folks. Our conversations in geometry lately have been about similarity. You can't talk about similarity without also talking about proportionality. So we've discussed ratios and proportions, and we reviewed what they are and how they're connected to similarity. But today we want to talk about four very important theorems that you might use or should be able to use whenever you discuss similarity or proportionality. The first one is the triangle proportionality theorem. It states that if a line parallel to a side of a triangle, so this is the line that's parallel to this side of the triangle, if it intersects the other two sides, then it divides those sides proportionally. And what this means is that side AE, if I divide it by side EB, then I should get the same ratio as if I were to divide AF by FC. So that line that's parallel to the third side divides those other two sides proportionally. Now the converse of the triangle proportionality theorem states that if a line divides two sides of the triangle proportionally, meaning AE over EB is equal to AF over FC, then it is parallel to that third side. So it's just the converse of the triangle proportionality theorem. So the claim here is that this line EF is parallel to that third side BC. And I understand that side BC is a line segment, but we're talking about the line that has segment BC in it. So if I were to extend this, then I could say that EF and BC, those lines are parallel to each other. Okay. The next one that we want to talk about is the transversal proportionality theorem. It states that if three or more parallel lines intersect two transversals, and it's not written on here, but I'm going to go ahead and mark these as parallel because that's what our hypothesis is using. It's three parallel lines. So if three or more parallel lines intersect two transversals, then they're going to divide the transversals proportionally. Meaning I can create the proportion AC over CE is equal to BD over DF. I could just as easily create the proportion AC over AE is equal to BD over BF. So that is an equally likely proportion that you might want to create. And then finally, we have the triangle angle bisector theorem. And that theorem states that an angle bisector of a triangle, so the angle bisector, it's bisecting angle BAC, so segment AD is the angle bisector. Because segment AD has cut this large angle BAC into two congruent smaller angles. So an angle bisector of a triangle divides the opposite side, and here the opposite side from this angle is side BC. So an angle bisector of a triangle divides the opposite side into two segments, BD and DC, whose lengths are proportional to the lengths of the other two sides. So the proportion that I can create is BD over DC. That's the pieces of this opposite side. And it's equal to the ratio created by the other two sides. So AB and AAC. Notice that BD is across from AB because they're both creating this other triangle over here, and then DC is beside AC. So DC, AC, because they're creating this triangle over here along with that angle bisector. So let's go ahead and scroll down and let's practice. We have 4 examples today. So in my 4 examples, if I'm trying to answer the questions, I can use either the triangle proportionality theorem, which starts out with 2 parallel lines. I could use the converse of the triangle proportionality theorem, which gives me proportional sides. I can use the 2 transversal proportionality theorem, which has to have at least 3 parallel lines and 2 transversals. Or I could use the triangle angle bisector theorem, which has to include an angle bisector. So there are certain things that have to be involved in the figures in order to use these theorems. So in example 1, I notice that I have parallel lines here, or at least parallel line segments. So that tells me I'm probably going to use the triangle proportionality theorem because that's the one that states that 2 lines are parallel in the hypothesis. So it asks us to find dg, the length from D to G. So this right here is the unknown. We're going to call it x. Now by the triangle proportionality theorem, I can say that this divides side EF and side EG proportionally. So I can create a proportion here of 32 to 24, and that's going to be equal to 40 over x. And I can set this up by, and I'm going to abbreviate, by the triangle proportionality theorem. Now, whenever I cross multiply, I have 40 times 24 equals 32 times x. Let's see, 32 and 40 are both divisible by 8. So this becomes a 4, this becomes a 5. And 24 and 4 are both divisible by 4, so this becomes a 1, this becomes a 6. So 5 times 6 is 30, and 1 times x is x. So my length from D to G is equal to 30. And there are no units that are given, so I'm going to leave the 30 as it is. So we were able to use these parallel line segments to create a proportion with the sides. Example 2 asks, are the segments parallel? So here we're talking about segment TU, which is right here, and segment RS, which is right here. Now we don't know they're parallel yet, but we'd like to prove that they're parallel, and I have some measurements out to the side. So that tells me I'm probably going to be using the converse of the triangle proportionality theorem. So let's see if we can create some ratios and see if those ratios are in fact equal. So I'm going to create my ratios, 67.5 over 54. And I'm hoping that it's equal to 90 over 72. So when I multiply those, when I cross multiply, I'm hoping to get the same number. So 90 times 54 equals 67.5 times 72. 54 times 90 is, let's see, 4 times 9, 6, 36, 45, 46, 47, 48, so 4,860. And then 67.5 times 72, I'll let you go ahead and type that into the calculator because I'm sure that you have one with you. If not, you can always use your browser, but it's also 4,860. So we find out that these are in fact proportional. And by the converse of the triangle proportionality theorem, if this line divides these 2 sides proportionally, then this line segment must be parallel to the third side. So therefore, TU is parallel to RS by the converse of the triangle proportionality theorem. Wonderful. Okay, let's look at example 3. Example 3 says find the length of each segment. I'm supposed to find the length of segment CD and AD. So CD equals, AD equals, and those are the two that I'm supposed to find. Okay, so I notice a couple things. I notice that I have either measurements or expressions for measurements on most of the sides. I also notice that I have this segment right here creating two triangles, and that this angle and this angle are congruent, and that certainly looks like segment CA is an angle bisector to me. So I'm going to ask you to pause your video, try to figure out which theorem you are to use, and determine the lengths of segments CD and AD. Pause your video. So hopefully you were able to use the triangle angle bisector theorem, which means that you can create 6 over 9 equal to y minus 1 over 2y minus 4. You could also create the ratio 6 over y minus 1 equals 9 times 2x minus 4. That would be all right as well. So when you do that math, you end up getting a y value of 5, and you're asked to find the length of CD and AD. So CD is 5 minus 1. That would be a length of 4. And AD is 2 times 5, which is 10, minus 4, which is 6. And then finally, we have example 4, which asks you to find the length of each segment. And so the segments that we have are MN and NP, and we have RS. We don't have QR, and we don't have, let's see, we don't have QR. We'll see what else we don't have in a moment, but we'll definitely try and find QR. Oh, I see. We have let's see, TQ, but we don't have TS. So we don't know this, and we don't know this. TS. Okay. So if I'm asked to find the length of each segment, I notice that I have 1, 2, 3 parallel lines, which looks an awful lot like the picture in the two transversal proportionality. And I have a transversal here and a transversal here. So kind of extend these. And the two transversal proportionality theorem says if 3 or more parallel lines intersect two transversals, then they divide the transversals proportionally. So I can create a proportion of 4 over 6. And that should be equal to, we'll give this a variable x, so x over 1. And this is by the two transversal proportionality theorem. So when I cross multiply, we have x times 6 equals 4 times 1, and x equals 4/6 or 2/3. So we have one value. Now if x's value is 2/3 right here, that doesn't really look like a length of 2/3 if this is a length of 4. In fact, this really doesn't look like a length of 1 if this is a length of 6. So I know that we've already kind of started our problem, but I'm going to amend part of our problem. And instead of this length being 1, it's a little bit longer than 6. I'm going to make it a length of 10. So I'm going to use 10 instead of 1. I'm going to put that here. And 4 times 1 was 4, but 4 times 10 is 40. And so this is 40 over 6. So my answer is 20 over 3. And no, I'm not going to ask you to do that in your problems. You would have no idea how to insert numbers. I'm just making a statement about how that didn't really make sense that much. And so I'm going to go ahead and make this 10, meaning that this distance right here is 20 over 3. Now, I've got one answer. QR's distance is 20 over 3, but now I need to find TS. And so now I have a second part of my problem. Now I have this angle bisector right here with my two angles that are congruent. And by the triangle angle bisector theorem, I can create a proportion. I can say that QR over RS, so QR over RS will be equal to QT over TS. And this is by the triangle angle bisector theorem. I'm really abbreviating now for the sake of space. So QR's distance was 20 over 3. RS's distance is 10. QT's distance, this right here, is 9. And TS's distance, we don't know that, we'll call it Y. So when we cross multiply, we get 9 times 10, which is 90. We get 20 over 3 times Y, which is 20 over 3Y. And in order to solve for Y, we're going to multiply by the reciprocal. So we have Y equals 3 times 9 is 27 over 2. And that's my distance from T to S, 27 over 2. So in summary, we can use proportionality and these 4 theorems to solve some complex problems when our figures look a particular way.